Hello and welcome back. Today we're doing 9-5 on alternating series. And the idea here is the sign flips for each term. So either all of the odds are negative or all of the evens are negative. So theorem 914 gives us what's called the alternating series test. So if we have either one of the two cases, either -1 to the n times a sub n, so this is a case where the odds are negative. So if n is 1, we have a negative, n is 3, we have a negative, etc. Or we can have the other case where the evens are negative. So if n is 2, we have -1 cubed, which is -1. If n is 8, 8 and 1, 9, -1 to the 9th is a negative, etc. So these will converge if both conditions are met. Condition 1, limit as n goes to infinity of a sub n equals 0. And condition 2 also has to be met, a sub n plus 1 less than or equal to a sub n, either for all n in the natural numbers. Now we do have the ability, like in the other ones, to remove a finite number of cases. So we can also use 0 is less than a sub n plus 1. So it's saying that a sub n's are still positive, less than or equal to a sub n for all n greater than some other n, cap n, and of course the natural still. So this is saying that maybe we have to go past the first 10 terms to meet criteria number 2, and after that we have a non-increasing series. It's written originally with just all n and n, but again, we can remove a finite number of terms and still apply this. We'll look at just a quick proof of this. So without loss of generality, you'll see that in math books. We'll use the one for the odds being negative. So that one again was the sum from 1 to infinity of -1 to the n times a sub n. And we'll assume that the limit as n goes to infinity of a sub n is 0, and that a sub n plus 1 less than or equal to a sub n. So then let's look at the sum of the first 2n terms. So that would be a1 minus a2 plus a3 minus a4 plus a5 minus a6 plus plus a sub 2n minus 1 minus a sub 2n. Hello and welcome. Today we'll be looking at section 9.5 on alternating series. The idea of an alternating series is that the sign is just flipping from one term to the next. So either all of your odd numbered terms are negative or all of your even numbered terms are negative. It's just flipping back and forth, positive, negative, positive, negative. Theorem 914 is the alternating series test. So this applies to either case. Sum from 1 to infinity, negative 1 to the n times a sub n. In this one, the odds would be negative. Negative 1 to the first is negative 1, negative 1 to the 97th is a negative 1, etc. This will also apply to cases where we have the evens landing on negatives. We just throw an n plus 1 in the exponent. So if n is worth 2, 2 and 1 is 3, negative 1 to an odd power is negative 1. So either one of these would be an example of an alternating series. These will converge if both conditions are met. Condition number 1 is that limit as n goes to infinity of a sub n is equal to 0. So we have to be dropping down to 0. And condition 2, a sub n plus 1 has to be less than or equal to a sub n. Either for all n in the natural numbers, or much like some of our work before, we can remove a finite number of terms and say, okay, after a certain point. If we're removing a certain finite number of terms, we're stating that we do have to stay on positives for the a sub n part of this. They do have to be less than or equal to the previous term, and this will hold for all n greater than n. So after the, say, 10th term or 15th term or 100th term, then this rule will apply for all of the ones after that. Cap n, of course, is some natural number since it's an index, really. Our proof, without loss of generality, that's an abbreviation you'll see more and more in your math classes the further you go. Without loss of generality, we'll use the case where we have the evens as our negatives. So this second one. So this is sum n equals 1 to infinity, negative 1 to the n plus 1, a sub n. We're going to assume that you have the case where the limit as n goes to infinity, a sub n is equal to 0, and that a sub n plus 1 is less than or equal to a sub n. So then we'll do the sum of the first 2n terms. So if n is equal to 1, 1 plus 1 is 2, even exponent, this becomes a 1 and we just get a sub 1. However, if n is equal to 2, 2 and 1 is 3, now this is a negative. And that will just keep happening. A3 minus A4, A5 minus A sub 6. Ooh, that is an ugly A6. And so on, and that will then keep happening until we hit A sub 2n minus 1 minus A sub 2n. Now what we're going to do with this is a little bit of rearranging. So I can also say that the sum of the first 2n terms would be a1 minus a sub 2 minus a sub 3. A quick check with that. The reason why that's working, go ahead and distribute this negative. You'll see that the signs for a sub 2 and a sub 3 do match up with what they are in the previous. A sub 2 would have a minus, a sub 3 distributing would have that plus in front of it. We can do the same thing with the next pair. A sub 4 minus a sub 5 minus dot 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 minus a sub 2n minus 2 minus a sub 2n minus 1 minus a sub 2n. Okay, so what did that do for us? Well, then that told us that our sum of these first 2n terms is less than or equal to a sub n for any n. I.e., the sums are bounded above by some limit L. So we'll call that limit L. So S sub 2n is a non-decreasing series, and it converges to L. If I take the limit as n goes to infinity of s sub 2n plus 1, that is the limit as n goes to infinity of s sub 2n plus the limit as n goes to infinity of a sub 2n plus 1. In other words, we take the previous sum and we add the next term, and that will give us the sum for the first 2n plus 1. Well, now I can say that the limit as n goes to infinity of the sum of the first 2n plus 1 terms is equal to, we know this converges to L, plus the limit as n goes to infinity of our 2n plus first term. But we know our 2n plus first term is going to go to 0 as n goes to infinity. So the limit as n goes to infinity of the sum of the first 2n plus 1 terms is worth L plus 0, which is equal to still L, our limit. All right, so let's see this in action. Now we've sort of played around with the proof a little bit. So let's look at the sum from 1 to infinity of -1 to the n plus 1 times 1 over n plus 2. So we want to see, does this diverge or does this converge using the alternating series test. So step 1 is examine a sub n, make sure it goes to 0 as n goes to infinity. So we'll do the limit as n goes to infinity of 1 over n plus 2. Well, my numerator is still, my denominator is growing without bounds. Sure enough, that is a 0. So far, so good. So next we have to show that a sub n plus 1 is going to be less than or equal to a sub n. Well, a sub n is 1 over n plus 2. That tells me that a sub n plus 1 is 1 over n plus 1 plus 2, or 1 over n plus 3. Well, 1 over n plus 3 is going to be less than or equal to 1 over n plus 2 for all n at least 1. And our index is, that's all we care about, our index is starting at 1. So for example, 1/4 is less than or equal to 1/3, 1/5 is less than or equal to 1/4, and so on. In other words, a sub n plus 1 less than or equal to a sub n. So we met both conditions, so this series will converge. Okay, so our next one, a little bit more challenging, but same ideas. We're running the same two pieces of the test. So we're going to do the sum from 1 to infinity of n over negative 3 quantity raised to the n. So first off, it doesn't look the way the rest of them do. However, we can simply factor negative 3 to the n as negative 1 to the n times negative 3. And 1 over negative 1 to the n is the same as negative 1 to the n. So sum from 1 to infinity of negative 1 to the n times n over 3 to the n. So that's our first step, is make it look right. Make it look like the other ones looked. So then we run the alternating series test. So first, I want the limit as n goes to infinity of our a sub n here being n over 3 to the n. Well, at the moment, we're in the infinity over infinity form. Notice that is appropriate for L'Hopital. So we'll have our friend Mr. L'Hopital help us out, and now we have the limit as n goes to infinity of 1 over natural log of 3 times 3 to the n. As n goes to infinity, numerator's holding still, denominator's growing without bounds. Sure enough, that's a 0 there. So far so good on the alternating series test. So then I want to show that a sub n plus 1 is less than or equal to a sub n. So this one, your author has kind of a clever proof for this. We know that we want some 3's involved and some n's involved. So the author starts us with saying that 1/3 is less than or equal to n over n plus 1. And as long as n is at least 1, this is okay. So 1 over 2, 1/2. A half is greater than or equal to 1/3. N equals 2, 2/3 greater than or equal to 1/3. 3, 3/4 greater than or equal to 1/3, and so on. We start getting closer and closer to 1. So this is going to be true for n at least 1. So then we rearrange this 1/3 in sort of a clever way. We know we want some 3n's or 3 to the n's and 3 to the n plus 1's eventually. So the author notices that 3 to the n over 3 to the n plus 1 will simplify down to 1/3. Just a quick little aside here of why that's working. If we have 3 to the n over 3 to the n plus 1, it's equal to 3 to the n over 3 to the n times 3 to the first. Remember, multiplying with the same base, your shortcut is add those exponents. And boom, there's a 1, there's a 1. 1 over 1 times 3 is 1/3. It's a little mathematical sort of sleight of hand trick. Nice little cute observation, very sort of clever manipulation. So the next thing we do is go ahead and clear those fractions out for a moment. So then we have 3 to the n times n plus 1 less than or equal to n times 3 to the n plus 1. Since n is at least 1 and 3 to any power is positive, we multiply both sides by a positive. We did not flip the inequality symbol. I might have made it look a little messy with my terrible handwriting, but we didn't flip it is the key point there. So then we kind of rearrange it into a version that we're looking for. We're looking to make it look kind of more like this. So I want an n upstairs and a 3 to the n downstairs. So I'll divide by 3 to the n. And if I do it on one side, I've got to do it on the other side. I'd also like this guy out of the way and move him over here. So we'll divide also by 3 to the n plus 1. Okay, so here's a 1, here's a 1. So now we're saying n plus 1 over 3 to the n plus 1 is less than or equal to n over 3 to the n. Well, notice this is a sub n plus 1, and this is a sub n. And we do have that less than or equal to relationship. And again, this is holding for n at least 1. So that is condition 2 met. So this says this series converges. Again, it doesn't necessarily tell us what value it converges to. It just tells us that, yes, this does indeed converge. I do want to look at a quick example where we wouldn't be able to use the alternating series, and we would have to then pick another test. For the sake of time, we'll just show that the alternating series doesn't work, and I'll tell you what test to apply. I'll let you work on applying it on your own. So we'll do -1 to the n plus 1, 3n plus 2 over 5n minus 6. So definitely an alternating series since we have a -1 to some power. So if we want to show that the alternating series test applies, I want to show that the limit as n goes to infinity of a sub n is equal to 0. But here this is where 3/5 not equal to 0. So alternating series test does not apply. For this one, I would recommend the nth term test. And you'll see that it will diverge. All right, that's the next one I wanted to take a look at. Alternating series remainder. The idea here is we'll use a partial sum to estimate a full sum. So our theorem 915. The situation we're in, we have to have a convergent alternating series. So if it's convergent, we know that a sub n plus 1 is less than or equal to a sub n. So if we have these conditions met, then we can conclude full sum minus the sum of the first n terms. In other words, our estimate. The difference between those, our goal of getting to the full sum minus our estimate, will be what we call the remainder. Not so super cleverly labeled as r sub n. Now our remainder is less than or equal to a sub n plus 1. All right, so an example. Sum from 1 to infinity, 1 over 6 to the n times -1 to the n plus 1. So in this one, we're going to approximate using first 4 terms. And then we'll find an interval that contains the sum. So we're finding S sub 4, so that's our S sub n. We're starting at 1 for our index, so the first term, 1/6, -1 to the second, plus n equals 2, 1 over 6 squared, -1 cubed, plus 1 over 6 cubed, times -1 to the fourth, plus 1 over 6 to the fourth, -1 to the fifth. So there's 1, 2, 3, 4 terms. So S sub 4, 1/6 minus 1/36, plus 1 over 216, and finally minus 1 over 1,296. Plug and chug on the calculator there, and we land at 185 over 1296. Decimal approximation. I typically don't use decimal approximations unless we're talking remainders or word problems. Approximately 0.14274691336. So our remainder we know is less than or equal to, that would be the next term. So the next term would be 1 over 6 to the fifth times -1 to the sixth, in absolute value anyway. Really, we would just concentrate on 1 over 6 to the fifth, 1 over 7,776, approximately 0.0001286, and some more stuff happening out there. We'll just go this far out. So this is sort of a bound on our margin of error. This is our maximum error here. So our true sum, somewhere between our estimate minus this and our estimate plus this. So we're between 0.142618, that looks like, and 0.1428755. So our true infinite sum is somewhere between those two. So we have a pretty good estimate, really just based on even our first 4 terms. These are in pretty tight. So then the next idea we talk about is the difference between absolute convergence and conditional convergence. So we'll start with absolute convergence. Which leads us to theorem 916. Sum of the a sub n's converges. So if we have this, then the sum without the absolute value also converges. So if we can make it converge when we ignore the alternating sign, then it also will converge with the alternating sign. Now we are conditionally convergent if the alternating one converges, but the one with the absolute value diverges. All right, so let's look at some of these in action. So we'll start with the sum from 1 to infinity of -1 to the n over cube root of n. So really where the action is okay, well, what is this thing doing? Is it converging or is it diverging? So let's look at that absolute value. So notice with the absolute value, this just becomes 1 over n to the 1/3. You may recognize that hopefully as a p series, so p equals 1/3. So if p is in 0, 1, we diverge. Okay, so we know that this thing diverges, so either the alternating series also diverges, or this is a conditionally convergent series. So we go to the alternating series test to find out. So condition 1, limit as n goes to infinity of a sub n. This guy, limit as n goes to infinity of, where are we? So -1 over cube root of n. And to the nth power. So we know that this is going to flip back and forth between negatives and positives, so we'll use the squeeze theorem. So this is between -1 over cube root of n and +1 over cube root of n. Well, this guy is going to 0, -1 over something that's going to infinity, that's going to 0, this guy's going to 0. So our limit is trapped between 0 and 0, our limit must be 0. So condition 1, consider it met. So then condition 2, this time condition 2 is a little bit quicker than condition 1. So a sub n plus 1 would be